Welcome to another edition of the Henstitute. For this one, we are going to be talking about the effect of electromagnetic waves when they strike some surface, and this is the concept of reflection. So when you have any kind of wave, actually, and it strikes some kind of surface, you're going to get reflection, which is the bouncing back of a wave. If you get really technical, what's happening is you have basically conservation of momentum as it has a collision with that and it comes off of there. So the idea of this is we're going to start off with just flat mirrors. So I have a flat mirror here, or sometimes referred to as a plane mirror, and then I have my eyeball up here. So the idea is I have this object. I have a knight from a chess table, and it's sitting in front of this mirror, and light is going to leave that particular object. So this beam right here is our incident ray of light. And we usually draw rays of light, even though we're talking about waves, and you say, well, shouldn't this be drawing like a wave here? Because that's what we just got done talking about, and that's true, but it's much easier to just draw the direction of it. So a ray is actually the direction it's traveling. And so as this ray of light leaves here, it's going to eventually strike this surface at a particular point B up here. And then after it hits that point, it's going to get reflected. It's going to bounce back. And so in this particular case, it's bouncing off of here and it's heading towards our eyeball. This is our reflected ray. And it reaches our eye, and that's what we see. Now, our eyeball doesn't realize that the light actually bounced off of that mirror. It thinks the light went straight. It tends to think that things go in a straight line, so light itself is going to do that. And so instead, what it's going to do is it's going to assume that that ray of light came from some point straight ahead. And so if we were to follow that and we get this point down here, what we find is the point on the object itself forms an image over here. And if you notice, what happens is the front of both sides is always going to be facing towards the mirror. And so since the front is actually facing towards the mirror, that's what eventually gives you that kind of flipping of left and right. You don't ever get a flipping of up and down because you're not actually changing the image itself, but you're just having the image always face towards the mirror. So that's why you have that happening. And so this is basically what happens when you look in a mirror. This is how you see an image. And we could draw a series of rays of light. We could have one come from the nose. We'd have one come from the top. We could have one come from the center. All these kind of bouncing off of here and reaching the eye. And each one of them would be just slightly different to kind of create your different points to go to the image here. So, you know, one of them would bounce off to the top of his head and one to his nose and so forth. The key idea that we are going to deal with in this is what we call the law of reflection. I think the law of reflection is probably the easiest of all of the physics laws, because basically what it says is that the angle of incidence, so put an I on there, so incident is what the I means, is equal to the angle of reflection. So the reflected ray. Now, what are we actually labeling when we deal with that? Well, someone decided that it was actually a physicist, a mathematician decided that it was actually better to look at a particular point, like point B, and don't actually measure the angle with respect to the surface itself. So we don't actually measure this angle. So this little beta 1 that they have down here, we don't actually tend to bother with that one. That is not our angle of incidence. Instead, our angle of incidence is actually this angle right here. And it's the angle between what we refer to as a normal. Remember, normal is perpendicular to the surface. So it's going to be perpendicular to your surface. So that's what this little dotted line coming out is. And it's the angle of the incident ray to that normal. So that's our theta I. And then it's going to get reflected over here. And so this is our angle of reflection. And it is the angle between the reflected ray and this normal. And so what it's saying is these two angles are going to equal each other. And because of that, yes, that it would be true. You would have an angle somewhere over here that would be equivalent to beta 1 down here. And so you could actually say that. But if this surface was not perfectly flat, if it was curved in some fashion, the only point that would actually reflect is right here. And it's much easier to measure with respect to a normal rather than actually to the surface itself. And so that is what allows us to get that. The other part that's kind of neat about reflection on a flat mirror is we have this down here at the bottom. I've got DO and DI labeled. And what they stand for is DO is our object distance. So the distance to the object. And then DI over here is the distance to the image. And when you're dealing with a flat mirror, the other thing you should always find is these two are equal to each other as well. In other words, your image is actually an equal distance behind the mirror, not actually on the mirror, but behind the mirror as your object is in front. So if you're looking at something and you think it's 5 feet away, but you're looking in a mirror, it will actually appear as if it's 10 feet away. So that's one way that actually looking in a mirror can actually be helpful, or something you could figure out that that object or that image actually is too far away when we're actually dealing with it. So this is the beginning of our little studies on things called reflection, refraction, and diffraction, different properties of waves, but specifically we're going to look at them in terms of electromagnetic waves, and we'll mostly kind of look at them in terms of light. Hope you enjoyed this edition of the Henstitute.